Welcome back. So this is our final lecture. There's only really two topics left for me to cover for us, and then I'll jump into the final review, which will occupy probably the majority of these sets of mini lectures for us. The two topics we're going to cover are complex eigenvalues and how we solve those cases with a system of linear differential equations, and the other case is how to solve systems of linear differential equations using Laplace transforms. Okay, so that's what's ahead of us for our final lecture, and then I'll move into the final review. So let's go ahead and jump right on in with complex eigenvalues. Eigenvalues. Okay, so this is a direct extension of what you already have seen in our in our previous lecture. So on this past Thursday, so the question is from our example, solve the following IVP. Okay, so that's what we're going to do. And the IVP, again, using the notation we saw from last week, uses the notation of matrices with linear algebra and differential equations. Here we have our coefficient matrix, 3, 9, -4, -3, the matrix X here for our unknowns, and then the initial conditions as well. And those should be two entries. In this case, it's 2 and -4. Okay, so the first thing we need to do, first step, we need to find the eigenvalues and eigenvectors for the matrix. Okay, so that will be our first step, and this is the first step I would expect you would do as well on your final exam. So to do that, we take the determinant of A minus lambda I, okay, equals determinant, and this is going to be 3 minus lambda, 9, minus 4, 4 there, minus 3, minus lambda. All right, and what this comes out to be, when you compute this, will be lambda squared, right, plus 27, okay? So this implies we have two lambda values, lambda 1, which is going to equal positive 3 times the square root of 3 times I, hence the complex root. And lambda 2 is just going to be the negative version of that, so that'll be minus 3 times the square root of 3 times I. Okay? So now that we have the eigenvalues, recall that we only need to get the eigenvector for one of the eigenvalues, since we can get the second eigenvector for free from the first eigenvector, since they are nearly identical in their solution. Okay, so we'll start with individual cases. Our first case will be lambda 1 equals 3 times the square root of 3 times I. Okay, let me go ahead and create a new page for you guys. All right, and let me get my pen. All right. So let me again just reiterate, the first case will be lambda 1 equals 3 times the square root of 3 times I. Okay? So we need to solve the following system. So with that in mind, we can solve the following system. All right, so the system is going to be, with our eigenvalue plugged in, it's going to be 3 minus 3. This should be a 3. Let me make that a little nicer. 3 minus 3 times the square root of 3 times I, 9, minus 4, minus 3, minus 3 times the square root of 3 times I. Okay, and our vector of unknowns here, which will be nu1 and nu2, and this should all equal the 0 vector. Okay, because we're finding eigen vectors here. All right, so this is a 0. All right. So using the first equation, we get the following. After you do the matrix multiplication, you get 3 minus 3 times the square root of 3, okay, I, times nu1, all right, plus 9 times nu2 equals 0, all right, and nu2 is then going to equal, right, so this is going to imply that nu2 equals minus 1/3 times 1 minus the square root of 3, okay, times I times nu1. So I solve for one of the unknowns. In this case, I picked nu2. And therefore, we can get our first eigenvector. So nu is going to equal nu1, all right? And then what do we get for nu1 in terms of nu2? You can see it here. Nu2 equals minus 1/3 times 1 minus the square root of 3i nu1, okay? So that's exactly what we place here. We get minus 1/3, all right, times 1 minus the square root of 3 times I times nu1. And there we have it. But to make this even easier to read and to interpret, you would say the following. Our first eigenvector, and we'd use the superscript of 1 to designate that, is going to equal 3, and that's going to be minus 1 after doing the distribution here, but the minus 1/3 plus the square root of 3 times I, okay, and here nu1 is set equal to 3, okay. So that's our first eigenvector. In the next video, I'll show you how you can get the second eigenvector and then how to put it all together. Stay tuned.